Number 10. Engine crash tests for massive airliners like the Airbus A380 are integral parts of aviation safety, designed to ensure the structural integrity and durability of engines under extreme circumstances. One of the largest passenger aircraft, the A380 relies on engines capable of withstanding various potential in-flight hazards. A key component of these tests includes the bird strike test, where engines are subjected to the high-speed impacts of bird carcasses. This simulates real-life bird strikes, assessing the engine's ability to maintain structural integrity and functionality. Given that each A380 engine can produce up to 70,000 pounds of thrust, ensuring they can withstand these impacts without catastrophic disintegration is crucial. Another critical test is the blade-off test, which evaluates the engine's containment capability when a fan blade is deliberately detached during operation. This scenario verifies the robustness of the engine casing in containing debris and preventing secondary damage to the aircraft's body and systems. Water ingestion tests are also vital, simulating heavy rainfall conditions. These tests ensure the engines don't suffer hydraulic lock and the turbines continue functioning, avoiding stalls or failure during actual stormy weather. Each of these rigorous and controlled tests provides essential data that guide improvements in engine design and materials. By pushing these engines to their limits, manufacturers can understand their breaking points and engineer safer, more reliable technologies for one of the world's most widely used modes of long-distance travel. Number 9. In 1988, a remarkable test crash took place that would serve as a testament to the advancements in safety engineering and understanding the dynamics of high-impact collisions. The experiment involved an F-4 Phantom jet, a relic of the Vietnam War era, purposely crashed into a massive, reinforced concrete wall. The objective was straightforward but daunting: to simulate a nuclear reactor's containment building's conditions and strength when subjected to severe impacts, such as a potential crash of a jet airliner. The F-4 Phantom, uncrewed and laden with sensors, was rocket-propelled at approximately 500 miles per hour toward the immovable object. In a moment of explosive destruction, the jet disintegrated upon impact, turning from a solid fighter aircraft into a virtually unrecognizable mass of wreckage within milliseconds. The concrete wall, measuring an impressive 3.5 meters in thickness, stood its ground. This test was not designed for the spectacle, though it was indeed that, but for gathering critical data. The sensors relayed information on the crash dynamics, including impact forces, structural behavior of the wall, and energy dispersion patterns. The catastrophic destruction of the F-4 Phantom provided a stark visual demonstration of the forces at play, emphasizing the need for robust structures and safeguarding against such high-energy collisions. The results were profound, contributing to enhanced safety standards in nuclear power plant design and offering invaluable insights into material behaviors under extreme stress conditions, thereby influencing future architectural strategies for buildings requiring high levels of security and durability. Number 8. In 1984, NASA undertook a groundbreaking experiment to enhance aviation safety that has reverberated through the decades: a controlled crash test of a full-sized airplane, specifically a Boeing 720. This event was part of the Controlled Impact Demonstration (CID), a joint research program between NASA and the Federal Aviation Administration (FAA). The dramatic test took place at the Edwards Air Force Base in California. The aircraft, loaded with crash test dummies and cameras, along with numerous sensors to record data on the crash's dynamics, was set to deliberately crash land. One of the experiment's primary goals was to assess a newly developed fuel additive's effectiveness, designed to reduce the fire risk associated with high-impact crashes. In a carefully controlled descent, the Boeing 720, flying on autopilot, touched down in a landing far rougher than any standard procedure. Upon impact at approximately 140 miles per hour, one of the plane's engines clipped the ground, leading to a breach of the fuel tank and, contrary to the experiment's intentions, a massive fireball. While the fire was an unexpected setback, the wealth of data collected was invaluable. The test provided insights into crashworthiness, post-crash fire suppression techniques, occupant dynamics, and potential means to improve passenger safety in survivable crashes. This intentional catastrophe helped set new standards in aviation safety and spurred advancements in aircraft design and materials used in their construction, making this controlled disaster a pivotal moment in ensuring passenger safety in the skies. Number 7. In a display of naval durability and technological prowess, the USS Gerald R. Ford CVN-78, one of the U.S. Navy's most advanced aircraft carriers, underwent a series of explosive shock trials. These trials are designed to demonstrate the ship's resilience and capability to withstand severe conditions on the high seas. The process involved detonating a series of controlled underwater charges in close proximity to the vessel. Each explosion was carefully measured, with the charges typically weighing thousands of pounds, to test the carrier's fortitude against shock waves and extreme force. The spectacle of water erupting near the ship, coupled with the vessel's massive displacement, is a testament to both the raw power of the explosives and the engineering marvel that is the aircraft carrier. Amidst these powerful blasts, sensors and cameras placed throughout the ship captured data in real time, documenting the effects of the shock waves on the structure and essential onboard systems. These tests are critical in evaluating the ship's battle readiness, ensuring that the vessel and its crew can withstand and continue to operate through near-miss explosions or under combat conditions. The shock trials of the USS Gerald R. Ford mark a significant phase in the ship's operational testing. The data collected will inform any necessary modifications, improve operational tactics, and shape future naval ship design, reinforcing the U.S. Navy's commitment to safety, preparedness, and technological advancement on the world's oceans. Number 6. In 2008, the television show Fifth Gear conducted an eye-opening demonstration that sent shockwaves through the perception of high-speed impacts. They crashed a car into a solid wall at a staggering 120 miles per hour. This experiment wasn't your standard crash test. It was designed to showcase the cataclysmic forces involved in a high-speed collision and emphasize the boundaries of vehicular safety measures. Upon impact, the car was horrifically disfigured, crumpling almost beyond recognition in less than a second. The violence of the crash rendered the usual safety features like seatbelts, airbags, and crumple zones moot, as they're typically designed for survivability in significantly lower speed collisions. Inside the car, crash test dummies bore the full brunt of the impact, graphically illustrating that human survival in such a crash scenario is highly unlikely. The test starkly demonstrated the sheer physics involved in high-speed impacts, underscoring that beyond certain thresholds, current vehicular safety technologies cannot safeguard occupants' lives. This dramatic demonstration was a wake-up call, extending beyond the spectacle of twisted metal. It reinforced critical messages about the limits of speed and the immutable laws of physics. The demonstration serves as a grave reminder to the automotive industry and drivers alike that flirting with extreme speeds comes with consequences that technology can't always mitigate. The relentless forces at play during such high-velocity impacts necessitate a conversation on responsible driving and continual advancements in vehicular safety for scenarios within the realms of survival. Number 5. In 2012, a groundbreaking event in the name of aviation safety unfolded in the Sonoran Desert of Mexico. An international team of scientists, engineers, and aviation experts came together for a daring experiment, deliberately crashing a Boeing 727 to study the impact and consequences of an airplane crash in a real-world scenario. This project was part of a documentary to provide the public and experts with insights into a plane crash's inner workings. The aircraft, equipped with sophisticated crash test dummies, high-definition cameras, and sensors, embarked on its final flight, piloted remotely by a chase plane after the crew parachuted to safety. The stage was set for an endeavor that was as much about scientific inquiry as it was about human courage. Hurtling to the ground at approximately 140 miles per hour, the Boeing 727 met its engineered fate in the desert. The impact was devastating that the front of the plane was completely destroyed, dramatically affirming the vulnerability of those in the front seats compared to the relative survivability of impacts for those located over and behind the wings. The aftermath was a treasure trove of data. The experiment unveiled a wealth of information about how the aircraft structure absorbs impacts, potential survival rates, and offered cues for improving passenger safety in future aircraft designs. This intentional crash has propelled forward our understanding of crash dynamics, emphasizing the profound need for continuous advancement in aviation safety protocols and technologies. By pushing the boundaries with such experiments, the aviation industry shows a commitment to advancing safety, where theoretical calculations give way to real-world crash scenarios, marking a sobering yet necessary step towards safer skies. Number 4. Sandia National Laboratories, renowned for cutting-edge research, has long been the epicenter of advanced testing in high-impact scenarios, particularly those involving rocket-propelled sleds. These specialized setups, critical in simulating high-velocity collisions, are integral to advancing military research and development. Captured at a staggering 10,000 frames per second, each test is a symphony of speed, impact, and precision. In a typical setup, sleds are equipped with various objects or experimental models and are then rocket-propelled down tracks at speeds often exceeding 600 miles per hour, mimicking the extreme conditions of a missile strike or an aerospace incident. These sleds, subject to monumental forces, collide into barriers, elucidating the breathtaking dynamics of ultra-high-speed crashes in a controlled environment. This high-resolution, slow-motion capture isn't just for show. It provides researchers with a detailed look at the split-second catastrophes often missed in real time. It's within these fine margins of impact that the secrets of material behavior, structural thresholds, and design efficacy are found. For military applications, this is invaluable. It translates directly into enhancing the survivability of structures, the safety of personnel, and the integrity of hardware subjected to high-velocity collisions. Moreover, while the immediate application is often military-focused, improving the fortitude of vehicles, the effectiveness of missile systems, or the safety of armor, the findings have broader implications. They feed into a global understanding of materials science and high-speed physics, contributing to advancements in civilian sectors like automotive safety and space exploration. In essence, the rocket sled impact tests at Sandia are more than just a collision at breakneck speeds. They are a confluence of science, technology, and purpose, with each test propelling our capabilities into new realms of knowledge and application. Number 3. In 2020, Volvo undertook a groundbreaking approach to safety testing by executing an extreme crash scenario. This rigorous test involved dropping new Volvo models from a height of 100 feet, aiming to simulate the intense damage and chaos wrought by the most severe accident conditions, far surpassing the common benchmarks of standard crash tests. The purpose of this intense trial was clear: to gather data in circumstances that mimic the very extremes of what a vehicle, and more importantly, the passengers inside could endure during a violent collision. These conditions exceed those in standardized tests, typically conducted at lower collision speeds. By subjecting the vehicles to such extremes, Volvo's safety engineers could study the immediate aftermath of high-impact crashes, analyzing the wreckage to understand more about the interplay between the vehicle's safety features under such stress. These insights are crucial for developing advancements in car safety technologies, focusing specifically on what happens in the split seconds of impact and the immediate post-crash phase. The real-world implications of these findings are substantial, informing enhancements in passenger safety mechanisms and structural integrity within the vehicle design. This daring approach reflects Volvo's enduring commitment to pioneering advanced safety technologies and their mission to ensure passenger safety under the most adverse circumstances. Number 2. In the pursuit of understanding high-velocity impacts in military defense, extreme railgun testing represents the pinnacle of controlled yet astonishingly powerful experiments. These tests, often conducted in secure, remote facilities, involve using electromagnetic force to launch projectiles at speeds exceeding 2,000 miles per hour, mimicking conditions that are out of this world. The science behind the railgun is as fascinating as the tests themselves. Unlike traditional weaponry, the railgun doesn't rely on explosives. Instead, it uses electromagnetic energy, allowing for a level of precision and speed that's unattainable with conventional firearms. When these projectiles strike their targets during testing, they offer real-time insights into high-speed impact scenarios, material durability, and ballistic science. The implications of these tests are far-reaching. For the military, understanding the effects of such high-impact collisions is crucial for armor and barrier development, ensuring maximum protection for troops and infrastructure. The data collected help engineers in designing materials capable of withstanding or effectively absorbing the force of incoming high-velocity projectiles. Beyond military applications, the principles tested in these extreme conditions inform broader scientific and safety considerations. The understanding of materials capable of withstanding these extreme scenarios can influence developments in aerospace, maritime construction, and even space exploration, contributing to advancements that may one day protect astronauts from micrometeoroid collisions. These railgun impact tests signify more than sheer force. They represent the merging of scientific understanding with practical, real-world applications, ensuring continuous advancements in safety, defense, and exploration. Number 1. The Bunker Buster, a pinnacle of military engineering, is uniquely designed for one critical purpose: to penetrate deep through fortified defenses and detonate its payload, where standard munitions have no effect. These specialized weapons are essential for modern warfare, capable of reaching hidden, subterranean military facilities and bunkers designed to withstand traditional assaults. One of the most striking features of bunker busters is their ability to penetrate thick, protective barriers. These formidable devices can bore through up to 15 feet of reinforced concrete hardening, a testament to their extraordinary power and precision engineering. This ability is crucial against underground fortifications, ensuring that strategic targets are accessible and neutralizable. Weighing up to 30,000 pounds, these munitions, like the GBU-57AB massive ordnance penetrator, are deployed from high-altitude bombers. They descend rapidly, harnessing gravity to increase their kinetic energy and ensure deep penetration. The impact is not just on a surface level. The shockwaves from the explosion can cause destruction deep within the target area, destabilizing foundations and destroying hidden, fortified structures. The bunker buster's value on the modern battlefield is unparalleled, especially in conflicts where enemies exploit underground facilities for protection, command, and control. By denying these safe havens, these munitions play a pivotal role in modern defense strategies, showcasing the blend of raw power and meticulous engineering required to maintain global security and counter hidden threats. I'm grateful you made it to the end. Your subscription is a huge motivation for me. If you like what you see, click subscribe and be a part of our journey.